Now I share my screen and we begin. So, welcome everyone to Miss Nami's room. I'm Miss Name. Take attendance in the chat and go ahead and rename yourself if you haven't already. The topic today is solvable versus unsolvable problems. And you might also see it written as decidable versus undecidable problems. I'll give you guys 30 seconds or so to change your names. Thank you, Sharma. Is it Deepika? Am I saying your name right? Aaron, Logan. Update your names. Nelson, Yasmin. Awesome, great. And then is it Taomi or Taomi? You can come off of mute. Noah, Shruti. Okay, so let us get started. This is the video that we just watched. The question I wanted you to consider is, can computers solve everything? And what was the answer? Decidedly no, right? So we just watched a short video about something called the halting problem, which is proof that computers and algorithms can solve many, but not all computational problems. And so the halting problem is an example of an unsolvable or an undecidable problem. And the question that the halting problem asks is, can you write a program that can, with 100% certainty, tell you if another program will run forever in an infinite loop, or if it will run and then exit? And Alan Turing presented this problem a while back. You don't need to know the details of how the issue works. All you need to know is that there are problems that computers cannot solve. After I speak, I'll be pausing for a little bit to give you a chance to make comments, ask questions, or just write down notes. I'll also be sharing these slides with you at the end of the lecture. So we know algorithms can't solve every problem, but there are some problems, many problems indeed, that can be solved in reasonable, aka polynomial time. That's something you should write down as well. Many problems can be solved in reasonable or polynomial time. So when I say reasonable, in mathematical terms, when we're being precise, we're talking about a polynomial sort of function, and we'll get deep into that. So don't worry if it doesn't make sense just yet. And so reasonable time means that the number of steps, the number of operations that the computer performs, or the amount of time required is less than or equal to a polynomial function, which is constant, linear, square, or cube as it relates to the size of the input. So this all may seem like a bunch of gibberish at the moment, but let's get into an example. That is a great question, Nelson. We can discuss after. So let's see some examples of reasonable time. Coming back to our slide really quick, I want to see, okay, we talked about constant, linear, square, or cube of the size of the input. So here's an example of a reasonable time where we have a constant runtime. You might want to jot this chart down. Just do a quick chart. On the left side, write input. On the right side, write number of steps. And so when we describe our inputs, we mean the number of, let's say, rows in a data set. More concretely, you might be a school administrator and your data set represents students and their ID numbers and the number of days that they're absent and their GPAs and so on, each column representing something else. Well, your input would be each row of that data set, so each student. So the question is, as we increase the number of inputs into our program, from 1 student to 2 students to 3 students, or in general, 1 row, 2 rows, 3 rows, what happens to the number of steps it takes our computer to do its thing, that takes our algorithm to complete? Well, notice that in this case, the number of inputs can go up, but the number of steps stays the same. And anytime you have something that stays the same, we use the word constant. It stays constant, it doesn't change. And that is a pretty dope program because you can have a huge number of students and it doesn't matter. The number of steps required is still going to be 3. So you can run it on 50 million students and you have still a very efficient program. And that's what we mean by constant runtime. It's always going to take 3 seconds or 3 microseconds. Now let's look at another example. This time, look at the number of inputs and look at the number of steps required. Can anybody find, and I invite you to come off of mute, can anybody find a pattern in how I would go from this number to get this number, from X to Y, or inputs to number of steps? What's the pattern that's jumping out at you? Yes, Shruti and Aaron both point out it's 5 times the number of the inputs. I have 1 input, multiply that by 5, it takes 5 steps. I have 2 inputs, multiply that by 5, takes 10 steps, and so on and so forth. Obviously, I made a calculation error here. 50 times, oh, no, that's fine. What am I doing? So yeah, it works out. And that's linear runtime because if you think about it, it follows the rule y equals mx, where my m, or my slope, is 5. And so I have a linear runtime. It's just being multiplied by the same number. I have the same slope. If we were to visualize this, it'd be a straight line. Okay, so now we're having more and more of an idea of what we mean by runtime. So here we have a square runtime. Notice that whatever the number of inputs I take, I'll square it and I'll get the number of steps. So 1 squared is 1, 2 squared is 4. If I have 50 inputs, I'll square that, 2,500 steps. So now we're starting to get into kind of an unwieldy sort of program that takes a long time. Especially as the number of inputs gets very large, you'll want to be very wary as a programmer. Oh gosh, this is going to require a lot of programming power and probably a lot of time. So square runtime is starting to get questionable. Then we have cube runtime. I'm cubing the number of steps. 3 cubed is 27, 2 cubed is 8. And I'm putting one final example up. Can anybody find the pattern? What am I doing? What is the rule that I am applying to X in order to get my Y? What is happening to the number of inputs? Noah, right on the money. Noah says it's not a polynomial like these were, x squared or x cubed, but here we have 2 to the power of x. Indeed, good eye, Noah. So we immediately recognized if I take 2 to the power of 1, I get 2. 2 to the power of 2, I get 4. 2 to the power of 3. So now the number of inputs is actually our exponent. Notice before the number of inputs was my base. I'm going to do this slowly just because it's so important. Here, the 1, 2, and 3, and the 50, and so on were down here, and they were being cubed. 1 cubed, 2 cubed, 3 cubed. In this case, the exponent, the number of inputs becomes the exponent. So it's 2 to the 1, 2 squared, 2 cubed. And while that might not seem like a big deal at first, as you get to higher numbers of inputs, look at how rapidly, look how quickly that number of steps explodes. So when we were being squared or cubed, we kind of stayed in what we will call from now on a reasonable runtime. These were reasonable numbers. Even when we cubed 50, we were still under 1 million. I can't even tell you what that number is. It's so huge, right? 2 to the power of 50, exponential functions grow exponentially. They grow incredibly fast. And so in the previous examples where we were squared, we were cubed, you can see that I added 3 steps for one additional input. And then from the second input to the third input, I added 5 steps. From the 50th to the 51st, I added 101 steps. If you do the subtraction, you can see how many additional steps are involved. When we cube, the number of steps that we add on for each additional input grows, but it's still manageable, it's still reasonable. Yet, when we arrive at the exponential runtime, and this is really key, even though the number of steps initially is small, we only add 2, and then we only add 5. Once you get into higher numbers of inputs, and you don't even need to go that far, 50 is not a big number, the additional number of steps just absolutely shoots through the stratosphere. And that's what makes this not reasonable. It's unreasonable. So I hope that that intuition makes sense. If we're to compare these runtimes graphically, this is a really famous kind of side-by-side layering of various runtimes. You'll see that our constant time, look at your x-axis first of all. This is the growth of our input, so the number of rows that you're analyzing. And then on the y-axis over here, what do we have? Algorithm complexity, which you can also see as runtime. So when it's constant, it doesn't matter what's your input amount, whether it's low or high, you're always going to have the same algorithmic complexity, which is quite low down here. For linear, we talked about visualizing as a straight line. We always know what we're going to get. It's going to grow by 5 if the slope is 5, or it's going to grow by 10 if the slope is 10. Regardless, it's going to be a straight line. But once we start squaring, we have a polynomial that's still reasonable. What is not shown, which I probably could show you right now, let me actually try this. What's not shown is what an exponential graph looks like, which would start down here, and it might be lower than the others at first, but it very quickly reaches this unmanageable and unwieldy amount. So this would be called big O of 2 to the power of x. And that's our exponential, which is totally wild. You never want to have an exponential runtime. You will be fired from your job as a programmer. Okay, and so another term, a fancy term, you might be wondering what this big O is. Big O notation is just a fancy way of saying what is the runtime. So we call this big O notation. Okay, I'm going to pause for 30 seconds. Any questions here before we move on? Okay, any questions? Type them in the chat or just jump off mute. I want to clear everything. Okay. Great, no questions. So let's move on. Now, this is what we've kind of discussed. Algorithms can solve many, but not all problems. And many problems can be solved in a reasonable time. That should now make sense. But some problems cannot be solved in a reasonable time. And some of those problems will involve an exponential runtime or a factorial runtime. Anything that, think of your math class, grows very, very rapidly when you look at the graph. Well, these are a special class of problems that are not necessarily unsolvable. They could be solved, but they just are unreasonable because they take a really long time. And so an example of that type of problem is the traveling salesman problem. Write this down. This is important. An example of a problem that can be solved, but not in a reasonable time, is called the traveling salesman problem. It's a very, very famous problem, and it's part of a class of problems called an optimization. Does anybody know what it means to optimize something, or what's it mean when you're looking for optimization? Any ideas? Any linguists in here? To adjust, kind of, but not totally there. Can we maybe optimize our definition? What does it mean to optimize? Yeah, so to find the best answer, to improve. Yeah, so to optimize is to adjust, but specifically to make it the best. So to get better and better until you reach that peak. That's what it means to optimize something. So maybe you've heard of the term self-optimization. It's the trend of like people making themselves more productive or whatever, right? I'm always trying to self-optimize. So let's have a look at what the traveling salesman problem is. Now this is, you don't need to write this down, just for you to know, okay? This is what the traveling salesman problem asks. Given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city and then returns to the origin city? That's what the traveling salesman problem is. It's basically, let's find the fastest or shortest route between all these cities. So we hit each one, never visiting the same one twice, but we end up back where we started. And you can imagine where this came from, right? The traveling salesman, before the days of e-commerce and Amazon, people went door to door selling knives and selling Bibles and whatever else they sold. And it was a real economic concern. How do I get from one place to another, visiting all the cities in the most efficient, most optimal way possible? So what I want you to notice is, here's a visual representation of our traveling salesman problem. Now have a look right now. Okay, it's trying to get better and better, right? So notice that this is generation 24, 25, meaning it's that iteration. It's trying, it's the 40th try, the 44th try. And notice that the length, it first, on the initial generations, it gets shorter very quickly. But after some time, once we get into the 30th try here, it kind of slows down. And that's just, it's kind of hitting a wall. Let me show you one more visual of the traveling salesman problem. And this time I want you to pay very close attention. This video is 2.5 minutes long. Okay, it's just 2 minutes. Pay close attention. And I want you to type in the chat what you notice when we're done. So keep your eyes open. type in the chat one takeaway or one thing you noticed or learned, or a question that you have from this video that we just watched. Was there a word that stood out to you? Something that surprised you? Is there a question that you still have? Take a minute and please type it into the chat. Usually in my physical classroom, this would be a time where we have a lot of discussion about the problems and the different algorithms that were suggested. So let's simulate that discussion. Yes, so Devansh says the number of possible routes was just absolutely massive. Yes, it was like something to times 10 to the power of a big number. That is huge. That means a lot of zeros, right? So there are a whole lot of possibilities. Noah noticed even if the computer made a good route, it doesn't mean it's the most optimal route, right? There could be a better one out there. And I want to talk about that too. Noah, good observation. Logan said the shorter and faster method is usually the least optimized or effective. Thank you, Logan, for sharing. Taomi said they kept making optimizations to make it better. Yes, with each step. And the way that they made those optimizations depended on the specific algorithm that was used, right? So there was one algorithm called the, what was it called? The 2-opt swap that said, hey, take 2 edges and swap them. And if it's better, keep it. If it's not better, don't move it. And so then it just kind of tries a bunch of different swaps and only keeps the ones that optimize. That was one way. That was one algorithm. Another algorithm said, hey, start at random and then make single changes until you get better and better and better. And okay, Shruti was explaining basically how optimization works in general. Yes, I really like the reference they made with the salesman, and I found it interesting. Thank you for sharing. There was one key moment that they talked about in this video, and I'm going to use my annotation feature here. This is really cool, you guys. It's the first time I ever used this drawing tool. Okay, so let's think of this as like a graph, where over here we have the like most efficient. So let's call it our run time. R for run. And that could be the number of steps, the number of seconds, anything that measures the efficiency. And then over here, I don't know what we're gonna do, but check this out. What if I had a graph that looked like this? Okay. Looking at this graph, we have multiple minimums. We have multiple local minimums. This is a local minimum because it's the lowest point of its surrounding region. This is a local minimum because it's the lowest point of its surrounding region. And here's another local minimum. And so while there are 3 local minimums, there is only one global minimum or one absolute minimum. And of course, that's this one right here. This is our absolute or global minimum. And so in the video, one thing that really stood out to me was there are some algorithms, particularly I'm thinking of the one that starts in a random orientation. Let's say it starts here. It just starts at a funky place. And then it wants to minimize the runtime or the distance. And so it gets to this point, and once it reaches here, and its runtime is, let's call it A, once it reaches there, it realizes that if it keeps changing, the runtime increases. So it settles on this as the best solution. And that is what they meant by settling at a suboptimal solution based on just the chance of where you began. You might settle on a non-optimal solution, and that is visualized as a local minimum. The same thing could happen if you started here. You might go down, and you'd settle at that point, thinking, well, that's the lowest point of the surrounding options, not realizing, of course, that if you just keep going a little further, you might get to this guy. And so that is the That is the challenge with some of these problems, like the traveling, like the traveling salesman problem. So let's move on. And so if you were to look for the absolute best solution to the traveling salesman problem, it's going to take you millennia. Okay, it's going to take even the fastest computers many, many years because of the sheer number of possibilities. And so instead of coming up with an absolute best answer, we might settle on a heuristic. I'm still trying to figure out how to say this word. And so one example was called the greedy algorithm heuristic. Write that down. Now, what is a heuristic? A heuristic is a solution that can help us find an approximate best answer in a reasonable time. In short, it's an approximation algorithm. So when we utilize a heuristic, we're recognizing that we might not get the best answer, the single most optimal solution, but that's okay because we don't want to spend our 80s and our 90s looking for the solution still. We want an answer in 5 minutes. And so we might settle for an approximation of the best algorithm and settle at a local minimum, if you will. So this concept of a heuristic is very important in computer science because we often encounter problems that cannot be solved in a reasonable time. And so in order to get a reasonable response, we settle on a heuristic algorithm that gives us an approximate best solution. Here is a formal definition for a heuristic. It's just the same thing I said. A heuristic is a technique for finding an approximate solution more quickly. And with that, I say, ooh, let's look at some hard problems. So this idea of hard problems that cannot be solved in a reasonable time also applies to modern cryptography. Nelson, that's a good question. You asked me, is that what modern GPS systems use? I don't know much about GPS, but I would encourage you to look into it. And then if you come to my next session next week on Tuesday, I'd love to hear your answer. So coming back, these not reasonable problems are called hard problems in computer science. And it also applies to the realm of cryptography. So this is taken from Wikipedia. Something called a brute force attack. This is an algorithm. And it basically says, let's try every possible solution. Remember that number times 10 to the power of something, that enormous number? Yeah, let's check every single one. That's what a brute force attack is. It's like, let's just go. Well, modern cryptography, the things that, keep your information secure, the uncrackable codes that keep your information private as it's sent across the internet, is protected by 256-bit keys. And so in order to break a symmetric 256-bit key by brute force, which means checking every possible solution, it requires 2 to the power of 128 times more computational power than a 128-bit key. And if you've done the unit on cryptography, or whether you haven't, it's okay. That's just an enormous amount of computational power required to do this many bits, to crack that many bits, versus a 128. And we are currently on this 256-bit because computers have gotten faster and faster. And so we need to make sure that we have really hard cryptography problems. What this means is that 50 supercomputers could check a billion keys per second, if such a device could ever be made, would in theory require 3 times 10 to the power of 51 years to exhaust the 256-bit key space, which means to go through each option. To put that in perspective, that's how many years 3 times 10 to the 51 is. I counted, I wrote out 51 zeros. That's a lot of years. So brute force attacks are not a reasonable solution. And so you might say, well, why don't we just use a heuristic? And to that I say, here's a question. Why would a heuristic be useful in finding solutions to some hard problems, like the traveling salesman, and not others, like cryptography? I want you to pause and think. Nobody type any answers yet, or you can type it out, but don't hit enter until I say go. I want everyone to think about this question for 1 minute. I'll repeat. Why would a heuristic be useful in finding solutions for some hard problems and not others? Think on it for 1 minute. Do not hit enter till I say go. We can take another 30 seconds or so. Remember, a heuristic is an approximation algorithm. Why would an approximation algorithm be useful in some cases and not others? 5 seconds, 4, 3, 2, 1. Okay, let's see some of your responses in the chat. Otherwise, come off of mute. Noah, you're invited to share your answer, to elaborate. Aaron also in the chat. Okay, I'm gonna read out Aaron's response. He says, with the traveling salesman problem, the good enough answers are good. We can settle on something that's good enough. But with cryptography, you need the exact bit. And if you used a heuristic, something that's close isn't gonna be helpful at all. It's still a wrong answer. Shruti agrees. With a heuristic, it's only for problems that can take approximate solutions. Excellent. And Noah, that's what you were getting at. Nelson, same thing. So is that, do I talk about it? Oh yeah, I think I put my notes in the comments. I say, heuristics are useful when an approximate answer is good enough. So for finding the shortest distance between locations, we can settle for a decent answer, even if it's not the best. But of course, with cryptography, we need an exact solution. Otherwise, wrong is wrong, even if you're just one character off. Beautiful. Thanks for thinking through that one with me. And so now let's dive into some multiple choice questions that are actual AP questions on past exams. The way we'll do this is I will put a timer for 1 minute and you will have a minute to mark your answers. So let me start the poll. Ooh, I don't have, oh, it's not working. Okay, never mind. We'll do something different. Okay, instead of a poll, we're improvising. You're gonna type in your answer, A, B, C, or D, but you won't hit enter until I say go. So I'll give everybody 1 minute to think. Which of the following statements is true? I'll give you a minute to think. Do not hit enter until I say go. Ibrahim, do not hit enter until I say go. That's okay. Well, it's totally fine. It's totally fine. I'm just kidding. Guys, 10 more seconds. Read through. And ready, set, go. What are our answers? Okay, so let's just focus on what makes A wrong. Every problem can be solved with an algorithm for all possible inputs. Right there, every problem can be solved with an algorithm. Wrong. We know of an example of a problem called the halting problem. We started class with that. That's the same reason B is wrong. Every problem can be solved. Again, there are problems in computer science. The halting problem is just one of them that is literally not solvable. It's not even about taking a long time. It's just, it cannot be solved. Okay, and so the correct answer here is D. There exist problems that no algorithm will ever be able to solve for all possible inputs. Great, that was a good run. Let's do another one. Hey, this chart looks familiar. Okay, let's put what we've learned to use. An online retailer uses an algorithm to sort a list of n items, these are the number of items, by price. So it's a sorting algorithm. The table below shows the approximate number of steps the algorithm takes to sort lists of different sizes. Based on the values in the table, which of the following best characterizes the algorithm for very large values of n? Take 1 minute, think through the solutions, the answers, and I'll tell you when you can press enter. Uh, 10 more seconds. Five, four, three, two, one, go. So just as I anticipated, we're split between A and B. So C and D, there's no reason to look at them. It's a sorting algorithm, so there is no reason for us to think it's an undecidable problem. There's also no reason for us to think that we need a heuristic here. I'm sure we can sort things, but A and B. Okay, so what is the rule? What is the runtime that relates the number of items or inputs to the number of steps just by looking at them? What is the rule? What are we doing to the number of items to get the number of steps? Right, we are squaring it. And so what you need to know is that x squared or even x cubed or even x to the power of 100, these are all polynomials. So polynomial, if we were to look it up, or if you're paying attention in your math class, is anything that has x as the base and any real positive whole number exponent. So this is, take this and it squares it. Polynomial runtimes are reasonable. Anything that's more than a polynomial runtime is not reasonable. So if it was like an exponential, like 2 to the power of x, that would be not reasonable. Or if it was like 2 factorial, that would be not reasonable. Or sorry, I mean x factorial. But since it's being squared, it's a polynomial runtime, and back from our notes, we said polynomial is reasonable. And so that's why the answer is A. Let me confirm that. Yep, the answer is A. So where was it in our notes? Right here. We said that these guys are reasonable. And then we looked at exponential, and that was absolutely wild. Exponential is not. Okay, so keep that in mind. Let's move on to the next question. A student wants to create an algorithm that can determine, given any program and program input, whether or not the program will go into an infinite loop for that input. That is literally the halting problem. The problem the student is attempting to solve is considered an undecidable problem. Which of the following is true? Take 1 minute and we'll discuss. As before, don't hit enter on your answer till I say go. Fifteen more seconds. Five, 4, 3, 2, 1. Let's see them. And by now, hopefully, you're recognizing that the answer is D. D is the answer. It's not possible to create an algorithm that will solve the problem for all programs and all inputs. Hopefully you got that one. Okay, let's look at another one. A certain computer game is played between a human player and a computer-controlled player. Every time the computer-controlled player has a turn, the game runs slowly because the computer evaluates all potential moves and selects the best one. Which of the following best describes the possibility of improving the running speed of the game? So we want to improve the running speed of the game. 1 minute on the clock. Don't hit enter till I say go. Ten more seconds. 5, 4, 3, 2, 1. Let's see them. Okay, so let us look. The answer in this case was B. B. So the reason why C is incorrect, it says the running speed cannot be improved because computers can only be programmed to find the best possible solution. And yet we went over what a heuristic is. And so we know that our computer programs can find approximate solutions because remember we looked at that wavy graph, and depending on where it starts, it might just fall at a local minimum instead of a global minimum. And as a result, that is an approximate best solution. The only way that it could find the best possible solution is through a brute force attack, which is going through every single possibility, but as we know, that would result in a really long wait time. And so our answer here is B. The running speed will be improved by using a process that finds approximate solutions, aka a heuristic. Good job, everybody. Let's do another. Which of the following programs is most likely to benefit from the use of a heuristic? And 1 minute is on the clock. Think about it. Which one of these would benefit from the use of a heuristic? Remember, a heuristic is an approximation algorithm. 10 more seconds. 5, 4, 3, 2, 1. Let's see them. And indeed, y'all got it right. The answer is, in this case, C. Okay, so let's think about it. A program that calculates a student's grade based on their quiz and homework scores. First of all, that doesn't require a lot of steps, so why would we need to approximate it? You just literally add numbers and then divide, right, to get the average. So that's too simple of a problem to even think of needing an approximation algorithm. B, a program, so A is out. B, a program that encrypts a folder of digital files. Again, not good for a heuristic. Like we talked about, encryption requires an exact solution. If you type into Google, try to sign into your Gmail and you have one character off, you might say it's an approximate password, but it's not going to work for you. So you will not benefit from the use of a heuristic in the realm of encryption, like we discussed earlier. However, using a program to find the shortest driving route between two locations on a map, aka the best route from point A to point B, very similar to our traveling salesman problem, isn't it? That's going to benefit from a heuristic, because even if the best solution is only going to take 8 minutes, if you take 8 minutes and 15 seconds, it's still pretty good, and you are going to be happy that you're not taking 15 minutes, right? So minimizing distances is definitely going to be benefit from a heuristic. Sorting numbers will not be good for a heuristic because there's literally only one right answer. There's only one right way to sort numbers from least to greatest. Let's do our last problem of the day. Just to make sure, yeah. Okay, last problem of the day. Under which of the following conditions is it most beneficial to use a heuristic approach to solve a problem? We discussed this earlier. I hope y'all get it. We're going to put 40 seconds on the clock. Ten more seconds. 5, 4, 3, 2, 1. Let's see them. Looks like the most popular answer is C. Let's see. When is it most beneficial to use an approximation algorithm? When a problem cannot be solved in a reasonable time. So that's the first thing. We don't want to use an approximation if A and B, if it can be solved in a reasonable time, because then we would just want to get the best answer. But it's down to C and D. When it cannot be solved in a reasonable time and an approximate solution is acceptable, that is a good time to use a heuristic. Very, very good. So guess what? we have concluded our lesson on solvable and unsolvable problems. We've looked at a variety of AP questions that tackle this exact question. And so what I'd like you to do is give me a thumbs up if you learned something today in the chat. Awesome. I love to see that. Really, really do.